We have some notation here. We've already talked about differentiation, and we had some notation that said take the derivative. This is the notation to say do the derivative, right? d dx of f of x means take the derivative. That's one of our notations for differentiation. All right? Again, that right there, there's what it means in words, take the derivative. Now, we need some notation for take the antiderivative of something. And take the antiderivative of something is going to be denoted with this notation. That symbol in front of it, that elongated S symbol, is called the integral symbol. Again, integrating is the word for taking the antiderivative. It's the directive. It's the action word. So we're going to integrate our function with respect to x. Now, in this, the integral symbol and the dx symbol kind of act as parenthesis pairs. Like you can't have one without the other. The dx part tells you what you're integrating with respect to. Just like up here, the d and the dx are together. It's differentiate with respect to x. And we did some implicit differentiation, so we know that the variables might not always match the one you're differentiating with respect to, right? So we could also have something similar with integrals, where the variable that you're integrating with respect to may not match the variables that you see in there, in which case the other variable in there would be a constant with respect to the other one. So just keeping that in mind, we'll work with that a little bit. Okay, but you always want to be integrating with respect to the variable, and those kind of just are parentheses around the function's inside of those two things. Okay. All right. So together, this matching of symbols, the integral of f of x dx, is the indefinite integral. There is such a thing as a definite integral. We'll see those a little bit later. This is an indefinite integral because it doesn't have boundaries that we would put on the integral. And a definite integral has numbers attached to the top curve and the bottom curve. We'll see those in a little bit, not in this section. But this one's an indefinite integral if you wanted to have its full proper name there. Okay? So it is equivalent to say that the indefinite integral of f is the antiderivative of f. The indefinite integral of f is the antiderivative of f. Again, just two ways of phrasing the same thing. If you're going to do the indefinite integral, you're going to do the antiderivative. So use this new notation to state the antiderivative from examples 2a and 2h previous page. Okay? So on previous page, 2a was, it gave us g of x equals 11x to the 10th. So in our new notation, instead of saying g of x equals this, find the antiderivative function, we would just say do the integral of 11x to the 10th dx. And so you would do that integral, and you would get x to the 11th plus c. So it's a different notation, way of saying the same thing, but instead of having to name the function and then name the antiderivative function with a new letter, capital G, I can just use the integral command to say do it and do it. Okay? So just checking out the new notation. So 2h, same thing. So if I wanted to do the integral of negative cosine of 4x dx, we already stated that that integral was going to be negative 1/4. There are notes up in the front if you just walked in to grab negative 1/4 sine of 4x plus c. All right. So for the most part, in the rest of the section, we're going to be working with this notation. Okay. So, rules. Okay. So we need some rules for our integration process, our backwards differentiation process. And so one of the rules that we already talked about, or thought about anyway, I'm going to flip my page back over while you keep looking at this page, is for the power type functions. Okay? In the power type function, we had to basically pull this power back up, right? And so we're going to be increasing the power by 1 at the same time dividing off that 11, right? So you can see the rule on the next page says if you're going to integrate a power function, whatever your power function happens to be, you need to, instead of multiply the power and subtract 1, we do the opposite. Add 1 to the power and divide, right? So that's the rule for power functions. It's the opposite of the differentiation rule, which was pull the power down and subtract 1 from the power to get the new power. We're doing the reverse. Add 1 to the power, then divide by the new power. Okay? That, of course, works for any power that is not -1, because if it's -1, all of a sudden the power became 0 and you're dividing by 0, that's not going to work, right? And we saw that what do you do if the power is -1? It's not really a power function. It's really going to integrate to natural log. So it won't work in the -1 power case. It's not a power function, but it does work for all the other variable, or all the other numeric powers. Okay, so using this rule, what is the antiderivative, or the integral, I'll read it that way. What is the integral of x to the 5th? So it's x to the, not the derivative, but the antiderivative, x to the 6th divided by 6 plus c. And again, if you do its derivative, bring the 6 down, the 2 6's cancel, power is 5. Take 1 off the power, you get back to the original, right? Okay. Since we're really good at derivatives now, we're going to be really good at checking our antiderivatives, right? Because you can just see, oh, yep, that goes back to that. So we got the correct antiderivative. Some people like to write it instead of over 6 as just 1/6 times x to the 6th. It doesn't matter. The rule just has it in the fraction form. You can leave it that way. Most people like to leave it that way once they get used to it. So, okay. Does that look good?
Where are you getting the 6 from?
Okay. So I'm actually using the power rule. So I added 1 to 5, yeah. And that's because if I'm going to differentiate this result now, I know that I would pull the 6 down, 6 times 1 6, then I would subtract 1 and get the original 5 that was up there. So derivatives, you subtract 1 for the power, so integration starts with adding 1 to the power. Yep, so power was 5, I added 1 and I got 6, divided by the new power, so divided by 6. Okay. A couple other rules right here. We mentioned this first one, the constant multiple rule, when we did, which one of these? When we did this one. Because we said that the 3 didn't matter, right? Because when you're going to do a derivative or an antiderivative, if you have a constant multiple, it just kind of comes on down because that wasn't really part of what you had to do for the derivative. You have to 3 alone to the derivative tangent to get secant squared. So you get to leave your constant multiples alone. Okay, that's what this rule here says. It says that if you have a constant times a function, you can take the constant out of the integral, ignore it, do the integral of the inner function, and then got your solution, right? Multiply by the c at the end. That's kind of what we did. Is we said, I'm going to think about that 3 later. Let's just do the derivative of the secant squared. And it was 3 times the antiderivative of the secant squared, which was tangent squared. Okay, so it's okay to pull constants out and deal with them later. They factor out of integrals. It's also okay to, instead of integrating both parts of a sum at the same time, to split a sum or difference into 2 separate integrals. You can integrate them piece by piece. We did that for derivatives, right? We said if we had derivatives, we could integrate one piece, then the next piece. You can do the same thing for antiderivatives. Okay? So, looking at these 2 examples, this one, because of the 14 there, I can write this as 14 times the integral of x to the 5th dx. Like basically what I'm saying is I can think about that 14 later and just do the x to the 5th part first, right? Because that 14 is a constant multiple. So rewriting it was kind of like showing that I'm thinking about it separately. And then my answer is going to be 14 times. I've already integrated x to the 5th up here. I know I'm adding 1 to the power. So that's x to the 6th over 6 plus c. And so I have 7/3 x to the 6th plus c. Okay, quick question about this. Is that 14 multiplied by the c or not?
Yes.
Yes and no. Yeah.
Attributive c turns out to be 0, then it'll still be 0, but if it was like 1, then it changes to 14.
Yeah, and so the idea is like if I use this rule and say, okay, you have a constant inside, this one would have 14x or to the 6th over 6 plus c, and this one would have 14 times. This one would have the parentheses because that 14's been pulled out of that whole thing. So it would say, you know, finish that whole thing, get your plus c. But the thing is, c is arbitrary, right? So it doesn't matter. This c and this c may not be equal, but they're both generic c's. They're both just constants. Because I don't know the value of c, it's still a number. Maybe this c is 14 times as big as that c, but they're still standing for an arbitrary constant. So just another note about that if you had to do c plus 100, it's still c. Because c is arbitrary. They may not be the same c on both sides, but it's because this c is arbitrary. So c is, that's the word up here, right? C is an arbitrary constant. So if you take that constant and multiply it by another constant or add a constant to it, you're still calling it just a constant. Okay? So we simplify by not having to write 14c when c is arbitrary in the first place. Okay? So c is arbitrary. It gets a little weird for us thinking about it for the first time because we're so used to in algebra having to make sure we carry through our distributes, making sure we keep coefficients in all of our variables. X is a variable, c is not a variable. It's an arbitrary constant, which means it gets to behave a little bit differently. So it's kind of cool. Something different to get used to, though. Okay? All right, we'll talk about the arbitrary constant over here again. This one, again, usually I don't have to rewrite to separate my integrals, but just to be extra clear with that property, I do get to do the integral of x to the 20th dx plus the integral of x to the negative 8th dx. Now, sometimes it's worth rewriting the integrals in separate integrals, especially if they're going to use different rules. So you can really see them as being separate because different rules may apply to each one. So you can just do one, then deal with the other one if it requires a different rule, right? But these require the same rule, so in most cases I wouldn't rewrite it. But again, just to think about each of them separately, the antiderivative of x to the 20th will be x to the 21 divided by 21 plus c, right? And then the integral of x to the negative 8th will be add 1 to x to the negative 7th divided by, and then you add c. Again, because that c is arbitrary, you don't need to add 2 c's. We don't usually add 2 c's. Usually we just add 1 c to the end because that c is arbitrary. This c that I wrote here isn't the same as those 2 c's. It's the sum of those 2 c's, but it's still an arbitrary c. So I only need to write it once. Okay? Yeah.
Where did the negative 7 go on?
I pulled the negative up in the 7 stayed just because positive and negative, I just combined into the negative.
Oh, okay, yeah.
Yeah. Yeah, it was just a simplification.
Yeah.
Yeah. All right.
Ends up the same too as 1 over 7x to the 7th.
Yeah, I mean, if you would like to write it even more properly, 1 over 7x to the negative 7th, or 7x to the positive 7th, I meant to say, would be perfect, right? I'm going to leave it alone right there. I don't need to write that properly right now, but that would be even better.